Right. Good afternoon, everyone. I hope you're having a great time at Build today. Thank you for joining us for this session. I'm Vishnu Charan, and I'm a product manager at Azure Storage, and I work on ensuring our storage platform can power some of the largest AI workloads. And I have Kyle with me.
Hi, everyone. My name is Kyle. I'm a software engineer on the Azure Storage Developer Experience team. We build libraries and tools for Azure Storage.
Thank you, Kyle. We'll call you back later.
Yep.
All right. In the next few minutes, we're going to cover the key needs of a storage platform for AI workloads. We're going to show how Azure Storage is going to address them or addressing them already, and show some cool demos along the way. Okay, Azure Storage is a massive platform which offers block storage solutions like disk storage, Elastic SAN, container storage, file storage solutions like Azure Files, NetApp Files, and Azure Managed Lustre, and object storage solutions like Azure Blob and Azure Data Lake Storage. And across all of these, Azure Storage also offers data management and migration solutions, and all of these are built on one common massive platform. Just to give you a scale of this platform, we transfer or read and write 200 exabytes of data every month, hundreds of trillions of objects, and hundreds of millions of DPS every month. And some of the largest Microsoft services use Azure Storage underneath. Let's dive into the Blob Storage platform and see how this solution enables you to build AI applications. Blob Storage comes with multi-protocol access, and this means you can inject large amounts of data across all of these protocols and eliminate data silos. And you can do this for both AI training and fine-tuning pipelines, as well as retrieval augmented generation or RAG-based LLM pipelines. Our integrations with Databricks, Spark, Hadoop, and many other solutions simplifies data preparation for these pipelines, AI training pipelines. And our BlobFuse 2 with scaled accounts brings terabits per second scale throughput directly to your GPUs, making sure the GPUs never sit idle. For RAG-based apps, Blob Storage is deeply integrated with AI tools like Azure AI Search and Azure OpenAI Studio, and even integrates well with popular open source frameworks like LangChain and vector DBs like Pinecone. And this helps ease the way you can experiment, develop, and deploy your applications. We have premium blobs that are 3 times faster than standard blobs, allowing you for low latency access on blobs. And they come with change feed and change notifications for making sure the data stays fresh for all your RAG applications. All of these features are built on common blob foundations, which means you get cost-effective tiered storage, you have multiple redundancies, and most importantly, it comes with security with Entra ID. Right. Let's look at how a common training pipeline looks like for AI workloads, AI workflows. For most of the AI tools, their unique capabilities start with the secret sauce, which is the data that they bring. And the data that they are trained on. This means bringing in large volumes of data from different sources, bringing them to one place, which is, in our case, Blob Storage, and then processing that data across multiple steps and arriving at a really high quality training data that can then be fed into training jobs. And when these jobs are run, you need to take checkpoints to save progress, and at the end of the job, you need to move that checkpoint or the completed model and store it back in your blobs, and then use it for inferences later. And this is a very clear example of this is OpenAI developing their model GPT-4o using these trainings and then inferencing it to run applications like ChatGPT. AI fine-tuning looks very similar, except you take an existing model, build domain-specific, you bring domain-specific data, and then fine-tune that model to handle scenarios more accurately for that specific domain. The rest of the process remains very similar. In this entire pipeline, for all of these to work really efficiently, the storage platform needs to support large scales of data ingestion, integrate with analytics pipelines for data preparations, and bring the data to the GPUs as fast as possible. And then once the training jobs are run, take that final data and or intermediate checkpoints and put it back into storage as fast as possible. And all of this also needs to be managed in such a way that the data is secure and can be handled in cost-efficient fashion. Now, these are not unique to AI alone. These are common for large-scale applications, HPC applications, even before AI. However, I want to focus on these two requirements that are more important to focus on for AI applications. First, the pipelines with expensive GPUs need efficient access to terabytes and petabytes of data, indicated as node local access. Second, the access mechanisms need to be extremely fast for both reads and writes to support checkpointing and bring the data back from those checkpoints. Addressing these requirements is vital for AI development as they directly impact the efficiency and success of your AI models. In this session, we're going to show you how blob storage addresses these two requirements, starting with the extremely high throughput. The first technology that I want to talk about is scaled accounts. Scaled accounts provide unlimited scaling of storage clusters across, and it expands your storage account across multiple clusters, which means you can access hundreds of petabytes of data on one single storage account, in fact, one single storage container. This is not a separate offering. This is not a separate SKU. These are just your normal storage accounts, and you can expand this to unlimited scale, terabits per second scale. In fact, we've used the learnings of this technology and expanded the limits of our default limits on our storage systems to 200 gigabits per second by default for egress. And when you need higher throughput, you can always bump it up using these scaled accounts to terabits per second scale. One of the largest users of scaled accounts is none other than OpenAI. OpenAI faces significant challenges in terms of the size of the data that they bring in and the complexity of the AI pipelines that they bring in. And checkpointing their models also involved distributed training clusters of GPU, causing large influxes of data. And any failures in this process means millions of dollars lost in GPU time, right? OpenAI leveraged Azure Blob Storage and scaled accounts specifically to access exabytes of data for their GPU nodes. And this reduced their operational costs and saved millions. And not only that, it gave them terabits per second scale throughput for running their training effectively. Great. We saw how the storage platform enabled high throughput access. Now let's focus on the other one, which is the GPU nodes and GPU nodes harnessing these high throughput access, right? How many of you have heard of BlobFuse? Right, not bad, a few. Okay, BlobFuse is an open source, Microsoft supported virtual file system driver that brings access to your storage account directly onto your Linux file systems. It's easy to install. It can bring scalable and massive cloud storage directly to VM environments, whether it is your virtual machine, these are your AKS containers, or even your laptop. Designed for massive scale data access, it supports high throughput access across both reads and writes, making it ideal for analytics, high performance computing, and AI pipelines. BlobFuse comes with two primary modes of operations. The first one is file cache that utilizes a local cache that you can choose to be your OS disk, NVMEs, or even your RAM disk, where it downloads the data from the storage onto that cache and then saves it to the application. This is extremely useful for AI training pipelines or when you need to reread the data multiple times. The second one is the streaming mode, which is what we call uses of block caching technology, where you can stream the data directly from the storage account. And we use chunking and prefetching mechanisms to read the data as fast as possible. This is extremely useful for data that may not fit in your system, or you want to read really large sets of data sequentially. And this is the go-to mode, especially when you don't have enough space on your memory. Right. Let's quickly jump to a demo to give you how BlobFuse works. Let's pick a common scenario among developers where you want to quickly access large amounts of data that's present in your shared storage and potentially run AI workloads on it. I'm going to mount a storage account a storage account container on my VM, access my files, read and write some really large files, and then show you how quickly Blobfuse uses. Okay. On the right, I have a storage account container for which, on which I have files that I'm going to use for this demo. And on the left is a VM on which I'm going to access my data. I'm going to access this data on an empty folder called Blobfuse mount, and I'm going to quickly mount this. I'm going to use the streaming mode, and it's as simple as saying streaming, and mount it. It's as simple as that. Just like that, I'm able to access terabytes, petabytes of data on the storage account on your local environment. Now, it's great to just access it, but what about the speeds that it can offer, right? You can see a couple of 50 GB files there. I'm going to try and read them. Before I do that, I'm going to use one of my favorite tools, which is endload. This shows live network traffic. And if you see the command, it is mapping the graphs to 35 gigabits per second, which is what my VM is rated for. Okay, let me go ahead and read those 50 GB files. All right, as you can see, the moment I asked it to read those 50 GB files, it is immediately maximizing the 35 gigs per second bandwidth. And what it's doing now, it's using this block cache technology that I spoke about, which is dividing this large file into chunks, prefetching them ahead of time, reading all of them in parallel, and serving it to the application that requires to read this file. And if you have really large files that require sequential reads, then this is the way to go. And just like that, we loaded 100 GB of data in about 23 seconds. This is not just for reads. You can do this for writes as well. So I'm going to write a couple of 20 GB files to the same folder. And I really love those cool graphs that go ahead and maximize 35 Gbps on the writes as well. This is the same technology that was doing for reads, except it's going to put it in buffer cache in memory and then process that data as fast as possible to the storage account. And just like that, we finished writing 40 gigabits of data. And this is a streaming mode, which means the data is already available in this storage account. There. You can see that the 20 GB file is already there on that storage account. This is massive because you can just connect to any storage account that you'd like and access really large files. All right, we wanted to show you how you can do this in not just one VM, but any computing environment across large clusters. And we decided to have some fun with it. So what we did was we picked up a bunch of compute nodes that are available to us and a really large buffer storage capacity on which we could write and read really large amounts of data with a benchmark, of course. We've done something similar before, if you've noticed one of our previous sessions, where we were able to achieve terabits per scale TBPS, which you saw in the previous note, right? So we said we'll go higher this time, and we got ourselves an Azure Cycle Cloud cluster with Slurm, a common environment that a lot of our AI customers use. And we got 325 nodes max at one stage, all of them Spot VMs, which are available. We just picked them. Round about 40,000 vCPUs at the time. Costs a bit of money, but we said we'll have some fun with it. My CVP is there laughing about it. But I hope it's worth it, because it's definitely worth it, and you're going to see it, right? And we wired all of these nodes to one single storage account with Blobfuse mounts. And the results were astonishing in terms of what we were able to do in less than an hour. We were able to set up and run this benchmark to achieve almost double the throughput of what we did last time, and we literally got 15.5 terabits per second just for writing the data, right? And for reading all of that back, it was an incredible 25.5 terabits per second. And as you can see from the Azure Managed Grafana dashboards there, these are not just peak throughputs. These are sustained throughputs. And we can go longer on this. And we just said, we'll just keep to this experiment, get this recording, and then get done with it. And at these speeds, you can download the entire Library of Congress, a 21 petabyte data set, in less than 2 hours. That is just massive. Yeah, thank you. To recap, we showed how you can use BlobFuse to access petabytes of data directly on your computing environment and then perform really fast reads and writes, and then expand that to really large clusters and still achieve terabits per second scale throughputs. Now, this is extremely important for enabling AI workflows. And let's take a sample look at AI workflow. Here's a sample of a multi-node cluster to access data from blobs. And usually, training data and checkpoints are present in different storage accounts or different storage containers of the same storage account. So we recommend that you use two mounts. The first one for mounting the training data sets using file cache. That means you can do repeated reads, especially if you have enough memory on your VMs. And then for checkpoints, use block cache that I showed you for writing to write data directly to the storage accounts. This means you don't have to store up all the checkpoints and waste your memory that are crucial for processing these applications. Right? Okay, let me show this in action with a demo. So while streaming is great for writing checkpoints, I'm going to show the data loading paths on the BlobFuse. So let's take a sample scenario where you want to use a specific checkpoint or a specific shard of it and load it for some quick inferencing tests, or maybe you want to fine-tune that model on a new node. Okay. Awesome. So I picked a Facebook OPT 30 billion parameter model, and I took a bunch of checkpoints. Here are a few checkpoints. They're essentially just copies of the model. And what we're going to do is load the last checkpoint that was available and then mount it and load it in such a way that it's available and prepped for running these large-scale trainings, right? Okay, so as I said, we can use file cache for this because it can load the model first or training data first and then do repeated reads. So I'm going to use the file cache mode. So this is the command for running this particular file cache mount, where I pick this folder called last checkpoint, where I'm going to load this or mount this particular checkpoint. And as you can see, I can choose subdirectories in BlobFuse, so you don't have to mount the entire storage container. So I can pick that particular directory that has that checkpoint. And if you see, the temp path is basically the cache space that I would like to use. And I'm using RAM disk that's going to make it as fast as possible. All right, the mount is now ready for me to access the latest checkpoint. Now, I need to load this checkpoint to make the model available. So I said, we'll go write a small script to do that. And yes, I vibe coded it with GitHub Copilot. And on the right, you can see GitHub Copilot explaining in its own words what this script does. Basically, it just takes the checkpoint that I pointed to from that mount and loads it, right? Before I run the command, I'm going to go back to the network view so that you can see what's happening when the model loading happens. So now, that script that I just showed you is loading this model using file cache from my blob storage account, right? The model is stored as safe tensors. And I have given it in FP16, and it has a maximum shard size of 5 GB. So that comes to about 13 files in total with 4.5 GB shards of the safe tensors, and then a few JSON files that you'd need for configuration and tokenization, right? And all of these are, of course, being read in parallel by the Hugging Face Transformers library, and no other optimization done. Just do a Hugging Face Transformer, use autoclasses, .pretain function, and this is how it works. And file cache does an amazing job. It just took 36 seconds to bring a 55 GB, 30 billion parameter model onto the local node and ready for inferencing applications. That is great. However, that still means you might get into cold start delays if your model gets evicted from the memory during any part of this process. And that's why I'm excited to introduce a feature called preload on BlobFuse. Preload warms up this cache and the data that you need before the application really needs that data. So what you have to do with preload is tell BlobFuse to say, go get me that data, and it's going to get that data, keep it ready for you. Let's see that in action. First, I'm going to unmount the checkpoint that I just loaded so that it's not going to use up the existing one. There, I've now unmounted the checkpoint, and I'm going to run exactly the same thing in terms of loading this checkpoint, except I'm going to use this parameter called preload. It's as simple as using that. And immediately after I ask it to preload, it is going to fetch the data really fast. Now, notice that this is as fast as the infrastructure supports, and it's already done. It downloaded 55 GB of data, like much faster than what the safe tensors were able to get to with the Hugging Face Transformers library. And this is even before the loading starts. So if I go back and try to load that model, let's see how fast that goes. So the model is already there, prepared for the application, and it loads in like 1.5 seconds, right? That's the power of preload, where the cache is already warmed up by the application. This is application agnostic, framework agnostic. You just ask BlobFuse to point to the checkpoint or any data that you need, training data, checkpoint data. It's going to bring it as fast as the infrastructure supports. Preload is available in preview today. You can go ahead and check it out at aka.ms/blobfuse. And this is going to eliminate cold starts for all of your new nodes, or if you want to bring up a new inferencing node, it's going to eliminate all of that. It has 20x faster reads to maximize GPU utilization. And as I said before, you don't have to have any code optimizations for these. And you don't have to mount the entire container. You can always pick and choose specific subsets of data that you want to preload. And preload is not just the only feature that we enable in the last few months. We've introduced more integrity checks into BlobFuse with CRC464 hash and ETAG validations. We introduced blob filters. That means you can say only a subset of blobs to be accessible at all times in a mount, irrespective if it is preloaded or not. It can be based on the last access time. It can be based on the type of files with suffix, prefix, name it. You will be able to filter that mount. And most importantly, we introduced something called autoconfig. You actually saw that in action, where I did not specify any config file. I just said use streaming, and I already set the environment variables to say pick from this storage account, and that's all it required. It'll automatically figure out what is the memory available on that particular VM, how many CPUs can you use, how much cache space that it can use. All of that it'll figure out and make sure it'll maximize the performance. And all of this can be done with CLI, which means it's easy to code it into any of your existing applications. Great. So you saw BlobFuse speeding up access to GPU nodes, and that's just one part of the story. We've been working on other tools to help you further in this space. So with that, let me bring in Kyle to talk about some of the exciting things that we've been doing.
Thank you, Vishnu. Okay, before we start, I want to get a quick poll of the room now. How many people here consider themselves a data scientist or ML engineer? You go ahead and raise your hand. Okay, a little bit. How many people here use PyTorch? Get a raise of hands. Awesome. Okay. If not, don't worry. I'll make sure to provide plenty of context so you'll be able to follow along and keep this content interesting. So while we believe BlobFuse is a great general purpose solution for integrating Azure Storage into your AI applications, when talking to customers, we've also seen an appetite for Azure Storage solutions that are Python only and tailored to specific AI and ML frameworks, especially with PyTorch. Specifically, we see customers wanting to stick with what they're comfortable with, that being Python and PyTorch, and want solutions that can fit that workflow without needing to add any new concepts that may be unfamiliar to them, such as a Fuse file system. With that being said, I'm excited to announce the preview release of the Azure Storage Connector for PyTorch. It is a Python library that provides PyTorch-specific integrations for connecting to Azure Storage. So with PyTorch, it provides many different building blocks for building and training your models. However, it does not provide built-in support for some common use cases involving Azure Storage, such as loading and training data samples and saving and loading your models all to and from Azure Blob Storage. So prior to the Azure Storage Connector for PyTorch, if you want to take a Python-only approach, that would mean that you'd either have to implement your own solution using the Azure Storage SDK or find an existing third-party library to use. So now with the Azure Storage Connector for PyTorch, it offers integrations for these common use cases such as data loading and model checkpointing all through Azure Blob Storage. And the interfaces of this library are simple in the sense you don't have to be too familiar with Azure Blob Storage in order to get started, and are directly consumable by PyTorch interfaces, which allow you to quickly plug in and continue to focus in on the model building and training. Finally, the implementations are performant. Specifically, they're faster than other Azure Storage Python libraries, including using the Azure Storage SDK directly through its public APIs. So now for the rest of this part of the session, I'd like to cover how to get started with the library and how to start using these features. So I've broken this part into 3 different sections. First, we're going to talk about installation configuration, and then talk about the 2 main features of the library. So starting with installation configuration. Because it is a Python package, all you need is pip to install it. So just run pip install az storage torch. Az storage torch is the name of the package. It's also going to be the name you're going to be using to import these integrations as part of your Python code. In terms of configuration, all you really need is your environment to be pre-configured with credentials. And this could be a number of things. For example, it could be a system-assigned identity, user-assigned identity, or even logged in using the Azure CLI. The library will automatically find these credentials and use it, so you don't have to explicitly set credentials in your Python code. So that's basically all you have to know for installation configuration. So let's talk about the first feature, blob.io. So when it comes to saving and loading models with PyTorch, there's 2 core interfaces you need to be aware of. There's the torch.load and torch.save functions. They both accept strings representing models to read and write your model to, and also a file-like object to read and write to as well. However, PyTorch itself does not offer built-in implementations for reading and writing models outside of your local file system. So now, blob.io, it's a file-like object that allows you to stream data to and from Azure Blob Storage. If you're familiar with other Python file-like implementations, such as Python's bytes.io or its built-in open function, it's going to be very similar. So the idea is that you can instantiate a blob.io instance provided directly to torch.load and torch.save for PyTorch to automatically load and save your model to and from Azure Blob Storage. And when it does so, it's going to do it fast. Specifically, it uses logic similar to the storage SDK for when blob.io is provided a large read or write. It'll break it up into smaller blocks and transfer it in parallel, which will reduce the overall time for torch.save and torch.load to complete. So let's go ahead and hop into a demo. Let's see. All right, so I have a Jupyter notebook planned out to help showcase how the library works. So I already skipped through the installation section. Specifically, I pip installed az storage torch. I also imported it. Notice it's the same name as what we use for the pip install command. And I also installed a couple other libraries we're going to be using later for the demo. So in terms of loading a model, here's a couple examples of how you would load a local ResNet model. It's used for image classification. So you can use torch.load and provide the string to the model, or we can also provide a file-like object. So here's us using open, specifying read mode, RB, and providing it to torch.load. And when we run this cell, what it's going to print out is the state dict. So this is representing the state of your model. So you can see the layer names and the tensors associated here. So once you have a state dict, you can then add it to your model by calling the load state dict method to give your model state and confirm that it was loaded successfully. So now, in order to use blob.io, all you need to do is import from the IO module blob.io, and the pattern used here is going to follow what you use for open. The only caveat is that you provide a URL to your blob instead of the string of your file path. So you can see here, here's a templated URL. I'm opening it up as RB mode for read binary. So I could either fill out these values with my storage account, my storage container, and my blob, or if I have access to it through the portal, I can just copy and paste it. So for example here, I have these ResNet weights, and I can go ahead and copy that to the clipboard, and then paste it into my Jupyter cell. And when I go ahead and run it, it should result in the same result as before. So you can see the layers and the tensors. All right, so let's talk about saving a model now. So when saving a model, it's the same pattern, it's just the reverse. So all we need to do is provide what we want to serialize. This is going to be our state dict. And then we can provide either a string to the file we want to save it to, or the file like object. So this is an example of how we use open. Notice that we open it as WB mode for write binary. We can run it, and it confirm that is in fact saved locally, and you can see these two weights saved. And now in order to use it for blob.io, the pattern is going to be very similar. All we need to do is provide our blob URL. Note that this is a different URL than we used before. I added the save portion, so it's a new blob. And also open it up as WB mode for write binary. And if I go ahead and run this, and then switch back to the portal, I can see, in fact, that we have our saved weights here. So now let's talk through a demo, show off the speed of blob.io. So I already ran this Jupyter Notebook cell before where it's loading the 5.4 model weights. And now we're going to go ahead and take blob.io and upload it to our Azure Storage container using torch.save. So I'm going to go ahead and run this and switch to the terminal now. And right now I'm running on an NCA100 v4 VM. It has 24 cores, 20 gigabits network throughput. And we see we're hovering about 10 gigabits per second. And that's fast in the context of, one, we're uploading as a single file and also as a file like object. So PyTorch itself is going to control how much we write and when we write. Specifically, when PyTorch serializes a model, it'll serialize the layer tensors one at a time and provide it to the file like object one at a time. And the cool part about what blob.io does is that it'll accept these serialized tensors and immediately return back from the write and upload it in the background, which will allow PyTorch to continue to serialize and write more tensors and overall decrease the time it takes for torch.save to complete. So now if I hop back into the Jupyter Notebook, you can see that it took 22 seconds for us to upload it. And also note that the CPU time is higher, and that's because we're uploading using threads. And I also ran this cell prior to the session to see how it compares to writing to our local file system. Specifically, we're writing to devshim. It's an in-memory file system based on tempfs, which will generally be faster than writing to disk. And you can see for this model, thanks to the optimizations, it's actually faster than writing to tempfs, which I find really cool. So that's about all I wanted to show for blob.io. The main takeaways I hope you got from it is it's simple. If you're familiar with Open, you really just need to replace your uses of file path with blob URLs, and it's also fast. All right, so now let's go ahead and talk about the second feature of the library, datasets. So when it comes to loading data samples with PyTorch, there's two main classes you need to be aware of. There's the dataset class, which controls how to retrieve and represent samples. And there's the data loader class, which controls how to iterate over the training samples as part of your training loop. And the idea is that you instantiate a dataset and provide it directly to your data loader. And with PyTorch itself and datasets, it doesn't offer too many concrete implementations of datasets. And the expectation is that you have to implement your own dataset or use an existing third-party library for your datasets. And when it comes to Azure Blob Storage and loading data samples, the story is similar. So prior to the Azure Storage Connector for PyTorch, that meant you would have to implement your own data set using the Azure Storage SDK, or find an existing data set implementation that hopefully supported loading from Azure Blob Storage as a feature. So now, with the Azure Storage Connector for PyTorch, it offers data set implementations that allow you to load data samples as blobs from Azure Storage. Specifically, it offers two concrete classes. There's the blob dataset, which implements a map-style PyTorch datasets. It also offers the iterable blob dataset, which implements the iterable style. And the difference between the two is that for map style, they're generally going to be smaller in size and can fit into memory, and you're going to be randomly sampled. For the iterable style, these are larger data sets that necessarily cannot fit into memory, and won't necessarily be randomly sampled. The idea is that when these are iterated through, it'll be iterated through it. The samples will be listed lazily as opposed to listed all at once. So in terms of actually creating a data set, there's two class methods that both classes offer. There's the from container URL, where for this one, you provide the URL to your container and list all the blobs for the container to build your data set. So the data samples returned from this data set will map one-to-one to the blobs listed. The second one is from blob URLs. With this one, you provide an iterable of blob URLs, and the data samples returned from this data set will map one-to-one to the blobs provided. This method is specifically useful if you have a preset fixed number of blobs that you want to use for a data set. It'll allow you to avoid making the list API call, or if you want to customize the way that your listing works in a way the library doesn't support, say, list all your blobs across a single storage account. So let's go ahead and go back into a demo of how this all works. So we're back in our Jupyter notebook, and we're going to be using the same container that we were using before. So I have, at the root of this container, a datasets prefix, and specifically I have the Caltech 101 dataset uploaded. This is just going to be images of various categories. So you can see the different categories here. I can click on one of them. And there's various different JPEGs for it. And let's show how we can use a library to access this data set. So in this Jupyter cell here, what I have is a map style data set created from the from container URL. Notice that it's different from the example in that we're providing a prefix keyword argument to only include blobs that are part of our Caltech 101 data set and filter out any of the models that were in our container. We can go ahead and run this now and see that we have 9,000 images in our data set. If we wanted to access one of them, we could just run this cell here and print it out. And what you'll see is that the samples returned by default are dictionaries representing the blobs in our data set. Specifically, this dictionary will have a key for the URL. So you can see this is a blob for a Dalmatian image. And also there's a data key here that represents the content of the blob in terms of bytes. So if we want to actually make sure it's an image of a Dalmatian, we can then take our content and throw it into Pillow and display the image. You can see, in fact, it is a Dalmatian. And now that we have the data set instantiated, we can then provide it to a data loader. We're going to be using all the defaults the data loader provides, such as batching, batch size. And when you run it, you can see that it's basically the same. The only difference is that the values are encapsulated lists. This is because we're using a batch size of 1. If we want more values in this list, we increase the batch size. So the one thing I want to point out is that your PyTorch models, they're generally going to expect the input in terms of PyTorch tensors and not necessarily bytes. So what you want to do is define a transform callable to get into the correct format for your model. So I have this cell right here that is going to take our Caltech 101 images and transform them in a format that can be interpreted by that ResNet model that we're using from before for image classification. And the idea when we define a transform function is that we need to provide a function plus one that accepts a single positional argument representing a blob in our data set. And this blob is going to just be effectively a Python data class, if you're familiar with that. So you'll have access to various properties on it. For example, you could get the blob name if you want. You can access the blob URL. And there's a couple other methods and properties that you have access to be able to perform the transform. So let's go ahead and walk through what this is doing by walking through the lines of code. Note that I have this URL here. This implementation is based off the recommendations from PyTorch. So first what we do is we call the reader method. This is going to open up a file-like object for reading the blob. This is just a blob.io under the hood. We're going to provide the blob.io to image, or Pillow to open up as an image. And then we're going to use a library called Torch Vision to then Torch Vision is a library provided by PyTorch for computer vision applications, and we're going to use it to apply the transforms we need based off the documentation, such as resizing it, cropping it, turning it into a tensor, and then normalizing it. And then finally, we apply all these transforms to get our image tensor back. And then finally, before returning the tensor, we're also going to return the category as just a sanity check. In order to do that, we can access the blob name. Here's an example of what the blob name will look like. So we're going to just split on slashes and then return the second and last component, which will be the category. In this case, it will be a Dalmatian for this blob name. So now to actually use the transform that we defined it, we just need to provide the transform keyword argument. And then also note for this data set, I switched it to being an iterable blob data set and also added the Dalmatian prefix so we want to get images of Dalmatians for our data set. So we can run it and get the first image, and you can note that it is a Dalmatian. You can see our tensor here. So now, just as a final sanity check to make sure it's all working, let's go ahead and throw it into our ResNet model. I just went ahead and put it in through a data loader, increased the batch size to 32, so we're getting more predictions for each iteration, and then provide it through to this ResNet model. And if I run this cell now, you can see that we have 32 predictions, and also most of them are Dalmatians. There's some other dogs mixed between, but overall, looks like it's working fairly well. And that about wraps up the demo that I had for data sets. And the main takeaways I hope you got from it is how simple it is to use. Really all you need to know is what style of data set you want, what your Azure storage resources are, and what's the transform you need. And that also about wraps up this part of the session. And I hope from all these demos, it really showed how easy it is to use PyTorch in Azure Storage using the Azure Storage Connector for PyTorch and motivated you to try it out today. If you want to learn more about the library, I recommend going to the GitHub repository. It's just under here at Azure Storage for PyTorch. And it has a link to the documentation for all the different integrations that we talked about. In terms of the Jupyter Notebook, I plan to commit it to this repository later on, so you'll be able to try it out yourself and play around with it. If you have any feedback or suggestions, I recommend opening up a GitHub issue in order to get in contact with us. Then finally, like I said before, this project is new, it's in preview, and we know there are likely other possible integrations with built-in PyTorch interfaces and other PyTorch-related libraries out there. So we'd love to hear how you are using Azure Storage and PyTorch today to help influence how this project grows, and also help influence what other AI and ML libraries we should consider targeting for tighter integrations for in the future. With that being said, I'd like to hand it back to Vishnu to wrap up the session.
Thank you, Kyle. That was a wonderful demo walkthrough, and it can be very useful if you're getting started. You have all the steps required, and I believe, Kyle, you'll be also sharing the Jupyter Notebook in the GitHub repository so that you can go ahead and try it out right away. Right? So to recap what we saw that we've developed a lot of new tools to help you get GPU node local access for all of your AI training pipelines. And for the other areas, we have other videos that will be linked to these sessions. You can go and check out how you can manage your RAG applications as well with a bunch of options. And apart from this, it's not just the AI workloads that we've been working on in terms of training and fine-tuning, but there are lots of new features that Blobs has been developing over the last few months. And the two things that I want to highlight is on the data management capabilities. Now, with AI pipelines, obviously the amount of data that everybody's holding onto is increasing massively, and with every AI innovation, it's going to generate tons of data. So in that context, we have two new releases that are going to help you manage those data. The first one is Azure Storage Actions. It is a no-code, no-infrastructure method of managing your data estate, however big it is. It might be billions of objects that you have in your storage account. You can just have tasks assigned to it, actions assigned to it, and say, pick a few items of this suffix or prefix and move it into archive within these days. All of that, you don't have to worry about setting up any functions or infrastructure. You can provide these instructions, and the pipelines will keep running as a service. Right? That's massive, and it also scales endlessly as and when your data expands. So please try out Storage Actions and give us more feedback. The other thing that I want to talk about is Storage Discovery. This is in preview right now, and it's available for private preview. Please do sign up using that link. Storage Discovery provides you a single pane of glass view of insights, especially long-term insights in terms of how your data is growing across multiple storage accounts. This is extremely helpful because it's not just one or two storage accounts where you have to go to each storage account, look at the patterns, or put it into pipelines or monitors. But this one collects across your entire data estates, shows you the trends, and helps you identify these peaks and lets you act on them. And it also helps you visualize security postures, redundancy lifecycle policies, and much more for your storage accounts. Of course, data management is also pivotal going forward for AI pipelines, so this makes sense to have more and more of these. We'll continue to innovate in this space. Watch out for more features. All right, for this session, here are some of the callouts. We have the GitHub repos for both the open source tools that we shared, Blobfuse, as well as the Azure Storage Connector for PyTorch. And if you have any feedback, you can always write to us. Or you can always connect on LinkedIn and reach out to both of us. There are other sessions that also talk about how Azure Storage enables AI applications, especially there's one on running stateful workloads at AKS. I want to call out that you can also see Blobfuse in action in that session, where there's going to be an AKS cluster running Ray, another machine learning framework, connecting via Blobfuse. So lots of innovations happening in this space. Please go check it out. Thank you, and I hope you had a good learning today.